Welcome to the workshop. Today we want to talk about section 9.1, which is sequences. And we want to start off with, of course, what is a sequence? Well, a sequence can be thought of as a function from the natural numbers or the positive integers, to the real numbers. So what that gives us is a list of things that are images of the function. So f of 1 is something, f of 2 is something, f of 3 is something, and so on. And so this gives us a list of numbers, an ordered list. And this ordered list can be represented by a sub n in curly brackets. So f of 1 would be a sub 1, f of 2 would be a sub 2, f of 3 would be a sub 3, and so on. So this represents the collection of terms in the sequence, or the set of ranges, or the set of outputs rather, from this function. That's what you can think of this as. So this is one of the terms. This is all of the terms. So an versus an in curly brackets. So let's take a look at an example. We want to list the first several terms of the sequence. We've got 4 examples to take a look at. The first one is given here. So if we wanted to consider a sub 1, we would simply plug 1 in for n. So this is our function. Our function is f of n is n over n plus 1. 1 over 2. A sub 2 is equal to 2 over 2 plus 1, which is 3. A sub 3 is equal to 3 over 3 plus 1, which is 4, and so on. We can continue this forever. So if I wanted to put it in the notation like this, I can identify the individual a values, or what I can do is I can put it in the notation using curly brackets to have 1/2, 2/3, 3/4, and so on. So this gives you a little bit of an idea. Again, a sub n is a particular value. This is the collection of all values. And this is the sequence. Excellent. For our next example, take another look at an example where the terms are given explicitly as a function. This is a function of n. So we have a sub 1 is equal to 1 squared over 2 times 1, which of course is just 1/2. A sub 2 is equal to 2 squared divided by 2 times 2, which of course is just 4 divided by 4, or 1. A sub 3 is equal to 3 squared divided by 2 times 3. So there's a common factor of 3 there that will cancel out, so we have 3/2. And this will continue on. Awesome. And it's perfectly fine to leave our response in this way. For the next example, it looks a little bit different. I don't simply have a sub n equals something. Well, I do, but I have a sub n is equal to 1/2 of a sub n minus 1. What does this mean? Well, this is a recursively defined sequence. So we have each term is defined by the previous term. So in this case, a sub 1 is given to us as 32. A sub 2 can be found as 1/2 of a sub 1, which is 1/2 of 32. Excellent. So this, of course, is just 16. I can continue on. A sub 3 is equal to 1/2 of a sub 2, which was 16, so 1/2 of 16. This is 8. And a sub 4 is equal to, let's see here, 1/2 of 8, which would just be 4. Now, in some cases, we'll be able to take a recursively defined sequence and be able to find an explicit definition for it. That is a function of n for the nth term. And if I wanted to do that, in this case, I can notice that I start with 32, and go to, let's see here, 32, 16, 8, 4. So as a side note here, I could write this as a sub 1 was a sub 1 was 32, not 16. A sub 1 was 32. A sub 2 was 16. A sub 3 was equal to 8. A sub 4 was equal to 4. And what I'd like to do is I'd like to find a way of representing the nth term without a recursive definition. I want to be able to write it explicitly in terms of n. So what I notice here is that this is 2 to the, let's see here, 5th power. And this is equal to 2 to the 4th power. This is 2 cubed. And this is 2 squared. So I know that each time I'm just looking at the number 2 raised to an integer power that's reduced by 1 every time. So a sub n in this case is simply given by 2 raised to a power. But what power is it? Well, when n is 1, it's 5. When n is 2, it's 4. When n is 3, it's 3. Notice 6 minus 1 is 5. 6 minus 2 is 4. 6 minus 3 is 3. So as I take 6 minus n, I get exactly the exponent that I'm interested in. So this is an explicit definition, or a definition in terms of n for the nth term of the sequence. Excellent. For our last example, this is also a recursively defined sequence, but instead of just being defined in terms of the previous term, f sub n is equal to the previous term, we actually include the term before that as well. So we have f sub n is equal to f sub n minus 1 plus f sub n minus 2. So any term is the sum of the previous 2 terms. In this example, we have to have the first 2 terms defined because we can't get to the third term until, let's see here, we can't get to the third term until we have the first 2 defined. So of course, f sub 0 is given as 0, f sub 1 is given as 1, and then from here we do the calculations ourselves. So f sub 2, beginning at 0, this is the 1, 2, 3, this is the third term. As I mentioned at the beginning of the video, this can be the natural numbers, it can be the positive numbers, or it can simply be the the natural numbers, the positive integers, or the non-negative integers. So including 0 is perfectly fine. And that's essentially what we've done here. So f sub 2 is the sum of the previous 2 terms. 0 plus 1 is 1. F sub 3 is the sum of the previous 2 terms. 1 plus 1 is 2. F sub 4 is the sum of the previous 2 terms. 2 plus 1 is 3. And the 5th term is the sum of the previous 2 terms. Or sorry, that's actually the 6th term, f sub 5. Sum of the previous 2 terms, 2 plus 3 is 5. And we can continue on in this way. This is called the Fibonacci sequence. It's something you may not have seen before, and that's okay. But it's something that you should be exposed to at some point. Fibonacci sequence. There is actually an explicit definition for the nth term of this sequence as well. It's a little bit interesting, though, something we will not work towards solving. There will be some problems where you might consider finding an explicit definition, but as far as we will be concerned, it will just be relatively basic examples like this one. I'll post some more videos pertaining to sequences shortly. We'll see you guys soon.